Today we're going to talk about curve sketching, and it's a pretty easy section. All you have to do is just remember what we've been talking about already, which is about the first derivative and the second derivative and what they actually mean. So I've already done the notes for you. Again, if you want to just pause the video, you can take notes whenever you're ready. But let's go through this again and really need to know this. Sorry about my boo-boos. The first derivative, that's what this is saying. If it's greater than 0, or even if it's written like this, a second derivative, that's what that notation means, is greater than 0. That means if you're greater than 0, that means you're positive. So if you're doing a sign test and you test and you're greater than 0 in the first or the second, there's two things that are going on. Then your original function, if your first derivative is positive, is increasing. If your first derivative tells us whether we're increasing or decreasing. If it's in the second derivative and it's positive, then we are concaving up. So when you see this notation, that's what that means. If it's the first derivative, it means it's increasing. If it's a second derivative, it means it's concave up. Now for the opposite is true. If it's less than 0, that means you must be negative. Your numbers are negative. Well, a first derivative value that has something less than 0 would be a function, the original function is decreasing. Whereas the second derivative, if that's less than 0, then that's saying I'm concave down. And so you need to know this notation. You need to understand what it's saying. First derivative refers to increasing or decreasing. Second derivative refers to concave up or concave down. And depending on if they're positive, positive would obviously mean increasing or concaving up. Negative would mean decreasing, concaving down. However, I can mix these. And that's what I want to show you here in this next little kind of cheat sheet picture here. I want to draw a function right now that is increasing, concaving up. So that would look something like this. Increasing, concaving up would look like this. Increasing, and then concaving up because it holds water. But drawing a function decreasing, concaving up would go this way. From left to right, we increase or decrease. Concaving up would hold water. Now the opposite is true here. How would I draw a function that's increasing but concaving down? How do I draw a function that's increasing, concaving down? So I would do from left to right, increasing, but then it would concave down that way. And then decreasing, concaving down would look like this. From left to right, I'm decreasing, and then I'm concaving down, I'm spilling the water. Use this as a guide on your quiz and on your homework. That should help you out to kind of curve sketch. All right, let's do an example that they'll show you on homework. Over which intervals of x is the first derivative greater than 0? Now, again, what does this notation mean? If I'm a first derivative, I'm either increasing or decreasing. If I'm a first derivative greater than 0, I'm increasing. So this means I'm positive and I am increasing. So if this is your f of x function, I should have said that. Where is the interval increasing right now? Well, looks like I'm increasing from left to right. Looks like I'm decreasing. Then I get about here, which is about -2. And then I start increasing until about 2 on the x. So from -2 to 2. Over which interval of x then is the first derivative less than 0? When is it negative? First derivative is negative when it's decreasing. So where is it decreasing? Well, from -infinity up to -2, it's decreasing. And then again from 2 to infinity. Now this question says, okay, well, from 0 to infinity, what is the function doing? Is it concaving up or concaving down? Well, 0 to infinity would be this way, and it looks like to me it's spilling water. So that would be concave down. So you'll have some quick questions like that. Pretty easy. All right, but let's look at 2 more examples and we'll be done here. Consider the function f of x equals 9 times x minus 5 to the 2/3. Find a critical point A, and then find where it's increasing, decreasing, concave up, concave down. All right, so again, we have to take derivatives. Increasing and decreasing is in the first derivative. Concave up and concave down is in the second derivative. So we're going to have to do both. Let's start with the first derivative. Derivative of the function would be 9 times 2/3 is 6 times x minus 5 to the negative 1/3, and then times the chain would be 1. I don't need to write it though. You must rewrite it as a fraction. So this would be 6 over x minus 5 to the 1/3. There's your first derivative. Notice we have a critical point right there. They call it A. So our critical point would be at 5. We're going to make a number line. We're going to plug these numbers into that first derivative. So pick a number that comes before 5, like 0. If I put 0 right here, negative 5 to the 1/3 is still negative. And this is always going to be positive. So positive divided by negative is negative. So in the first derivative, if I'm negative, I am decreasing. Let's put a number like 10 in. Well, that would be positive over positive, which is positive. So I am increasing. So you would say I am decreasing from negative infinity to 5, and then I'm increasing from 5 to infinity. Very simple. All right, but to find out concavity, I have to do a second derivative. So I'm going to do a second derivative. I like to take it from up here. So 6 times negative 1/3 is negative 2. X minus 5 to the negative 4/3. And then rewrite that as a fraction, negative 2 over x minus 5 to the negative 4/3. Once again, I have that 5 as a point. Could be a possible point of inflection, but it looks like up here it's definitely decreased to increase, so it's definitely a min. But it's still an important point, which I'll show you when we look at the graph. So 5, if I pick a number that comes before 5, like 0, that would make negative 5 to the, whoops, that shouldn't be negative. That should be negative 5 to the positive 4/3. Negative 5 to the positive 4/3, a lot of students get wrong. They think it's negative, but to the positive 4/3, it's a positive number. So I have a positive number on the bottom. I always have a negative number on top. So this is negative in that section, which in the second derivative, if I'm negative, I am concave down. Now, if I pick a number after 5, so let's say like 10, 10 minus 5 is positive. To the 4/3 is still positive, but on the top it's negative. Oh, I'm negative again. I'm concave down again. So let's just real quick take a look at what this picture looks like. And here's actually how you should write it. Concave down from negative infinity to 5, 5 to infinity. You actually don't want to say the whole thing because something's happening at 5. And if we take a look on Desmos, here's the original function, 9 times x minus 5 to the 2/3. Look at that. There's a cusp happening at 5. Okay, so this function, as you can see, is concave down. Now, this is not concave up. I know I usually use the phrase, it holds water, and it looks like it's holding water, but I'm saying holds water to help you realize when you have a continuous function, when you have derivatives that you can take at every single point. When you can't take this derivative, this part right here is not really holding water. So it's concaving down, and then it's concaving down again. And that's what the picture looks like. So quite interesting. Let's do one more. So this one is where you have f of x equals x squared times e to the 8x, and they're telling us it has 2 inflection points. So right off the bat, you know you're going to have to do a second derivative because inflection points are in the second derivative. And then it even says, where is it concave up or down? So that's in the second derivative. Inflection points are when you change from a concave up to a concave down. This is not an inflection point. It did not change from concave up to concave down or vice versa. So what are we going to do? Well, we need to take a first derivative. Oh, but look what we have. It's a product of 2 functions. So we need to do product rule. So let's do product rule first times the derivative of the second would be, you write it again, and then times this chain. So 8e to the 8x, first times derivative of the second, plus the second times the derivative of the first. Now I like to rewrite this. So I'm going to rewrite this as 8x squared times e to the 8x plus 2x e to the 8x. Now you could do, again, you're going to have to take a second derivative. So you could do a product rule here and a product rule here, which some students do. But I might just factor out, and I'm actually just going to factor out an e to the 8x. And then just do one product rule with those two. So let's do that. Let's take a second derivative. So first times the derivative of the second, this would be 16x plus 2 plus the second times the derivative of that, which is 8x again. Now you do need to clean this up because remember we're looking for inflection points, which means we're going to have to set it equal to 0. So let's kind of distribute and clean it up. So I would actually rewrite this as 16x. I like my e's in the back, e to the 8x. And then this would be 2e to the 8x. Then I'll multiply this. This would be 64x squared e to the 8x. And this one would be 16x e to the 8x. Well, I actually already have one of those, so I'm just going to combine those like terms. And since I have some square terms, I'm going to put them in order. So I'm going to write 64x squared e to the 8x first. And I'm going to put 32x e to the 8x. And then I'll write my 2e to the 8x. And remember, we're solving for 0, so I'm going to factor out a 2e to the 8x. And I'm left with 32x squared plus 16x plus 1. Now, trying to find inflection points, set it equal to 0. So we were going to set 2e to the 8x equal to 0. Divide by 2 would be that. How do you undo an e? You ln it. Well, you can't take the ln of 0. That's not true. So that's not our inflection point. These are our inflection points. And I hate to tell you, but this is a quadratic formula. But I want to show you a little trick. So if you remember back when you did Mat 171, you could go to, in your newer calculator, the apps button. And there is a button called Poly Simulator 2. If you don't have this, you're going to want to get one. And you can do Polynomial Root Finder. And this is a degree 2. And we're going to hit next, which is graph. And I had already put it in 32, 16, and 1. You would just put your coefficients in and hit solve. And you can, in My Open Math, just write those decimals. So it's found both of those those inflection points for you. Negative 0.42678. And then negative 0.0732. Those are the 2 points C and D. Let's see where it's concaving up and concaving down. So on a number line, you're going to put negative 0.42 here. because it's further away from 0, and then negative 0.07 here. And you're going to test a point. And so I would test like, I mean, to the right of this would be 0 or even like 10, because this side is negative. So that would make all of these positive. So this is positive. And again, this is a triple one. So it's going to go plus, minus, plus. So this is concave up, concave down, and then concave up again. And you would write them out with interval notation. But just to see how cool this graph looks like, because you'd be like, how does this actually look? If you go right here, and I've already put the original function in, you're like, oh, it just looks like it's, holding water the whole time. But if you zoom in, look at that. It's literally holding water, dumping water right here, holding water after that. I mean, that is a very interesting looking graph. So sometimes it's neat to look back at your graph. But Poly Simulator, guys, that is, use your calculator, use that Poly Simulator and it's underneath the word apps. And that'll help you. And again, you can plug that in and then write your intervals of concavity. Hope that helps. See ya.